Aloha and welcome to our video on atmospheric characteristics. In this video we will compare and contrast weather and climate, we'll identify the properties of the atmosphere, and we'll explain why seasonal changes occur. So taking a look at this graph here, what we're showing is the volume of clean dry air. So if we went out and we collected a sample of clean dry air, what the dry means is we take the humidity out of it, and what the clean means is we take the pollutants out of it. What we would end up with naturally is this graph here, and this kind of shows us what our different percentages are of the components that make up our air. Now, as you can notice, most of it is going to be this nitrogen down here, and that's what most of our atmosphere is. The part that's important to us is this oxygen, and that's right up here, and that's what we use to breathe, as well as most organisms do. This one was kind of biologic in nature. Once we had the first photosynthetic organisms going, they converted this carbon dioxide portion here into oxygen. And you can see there's still a little bit of carbon dioxide left. We have a lot more oxygen now. We have some argon, and then we have some other elements out there as well. So this is what our air sample would be like if you were to go out and just collect a sample. Most of it, once again, is going to be nitrogen. There's a large oxygen component, and then there's this carbon dioxide component, which will come into factor later on. Okay, so in the last graph we looked at, we said it was a clean sample. And we know if we were to go out and gather air from Las Vegas, it's not exactly going to be clean. We're going to have some pollutants inside. So these two graphs are going to discuss some of these primary pollutants. If we look at what they are, we'll notice that most of it is going to be carbon monoxide. About half is carbon monoxide. We also have a lot of sulfur oxides, and then we'll also have some nitrogen oxides, and we'll have our particulates, which would be like our dust, things of that nature, and then finally we have some volatile organics up here. Mostly we're going to be concerned about, we're going to be these and these two here. The carbon monoxides, if we go to the other side, you can see that about 46% of our pollutants come from transportation. We also have stationary fuel combustion, which is another 23%. So that would be like our coal burning power plants. We make a lot using the industrial processes that we have. And then we have our miscellaneous, whatever it falls into, and our solid waste disposal. This would be like if we were burning trash. We get about 2.5% of the pollutions come that way. So you can see a correlation between some of these. The carbon monoxide we'll talk about a lot. We'll also talk a little bit about these sulfur oxides. We covered them last semester when we talked about acid rain, and that's where we're getting some of the acids for this to occur. So our pollutants, you can see where they're coming from and then about what they are. And that's what we find in our air if it's not a clean sample. Okay, so in this graph, what we're going to look at is changes in atmospheric pressure with altitude. When we're talking atmospheric pressure, we also sometimes call it air pressure. And we'll talk about that a little bit more in this unit on weather. But air pressure, quite simply, means that it's the pressure of the air that we feel upon us. And we're going to focus primarily on this downward sense because we can look at air pressure as being this column of air above us. And if we look at the graph, we realize that most of the air is going to be at a lower altitude. So what we'll notice is we see this here, we can put in our air molecules, and you can see how it kind of thins out a little bit as we get up higher. So the higher in elevation, there's less air pushing down on you, so you're going to have less pressure upon you, and that's what this graph is kind of showing us. So if we have a significant change in altitude initially, we're going to see a greater change in the pressure, versus as we get higher, that change in pressure is going to be a little bit less and less as we go up. Now in this graph, we're looking at thermal structure of the atmosphere. Basically, how does temperature vary as we travel up through the atmosphere? And we'll notice a bunch of different things. As we go here is 32 degrees Fahrenheit or 0 degrees Celsius, and this is going to be where water freezes. And then we're going to get warmer here and then cooler on this side here. We also see that we have our layers of the atmosphere. So our layer that we live in is the troposphere, and that's the lowest layer. Above that, we have the stratosphere, the mesosphere, and the thermosphere. And we'll talk more about the layers of the atmosphere in the lessons as we go on. One other thing I want to show you is we have this maximum ozone here. So when you hear about the ozone layer, this is what we're talking about. So let's look at the general trends that we have. If we start on the surface, we'll change over here. If we start on the surface of the Earth here, as we travel up, what we notice is it's going to get cooler. So that's why if you go up to Mount Charleston, it's always going to be a little bit cooler here in Las Vegas because as elevation goes up, it gets a little bit cooler. Once we cross into the stratosphere through the tropopause, what we'll notice is that the temperature kind of levels off a little bit, and then we see an increase in temperature up to the top of the stratosphere. And that's primarily because above the ozone layer, we have a lot more cosmic radiation occurring. The ozone layer stops UV light, so we're getting bombarded with more of these particles, and that's going to warm up the atmosphere a certain degree. Once we get into the mesosphere, we'll notice that the cooling trend is going to continue again. And then we get into the thermosphere, and in the thermosphere, we'll see that it's going to extend upwards and our temperature is going to get warmer. And this might lead you to think that space is going to be warm, but in reality, once we exit the atmosphere, it gets really cold in space. This here is just because we're going to have more cosmic radiation occurring. So we can see that by the ozone layer here above that, we notice a warming trend, and then we start to have this cooling again, and then we'll see the warming trend again because we can have more radiation occurring in the upper layer of the thermosphere. Okay, so when we talk about the Earth's axis and its tilt, this is what's going to give us night, day, seasons, things of that nature. So let's take a look at some of the motions and the importance of part of these things. The first motion we're going to talk about is rotation, and the result of rotation is the day. It takes 1 day for the Earth to rotate on its axis, and as it does so, it's going to spin around like this, and it allows the Earth to have periods of heating and cooling. So you'll notice that half of the Earth is going to be heating up, it's going to be daytime, and the other half it's going to be cooling off when it's nighttime. The second motion is revolution, and the net result of revolution is the year. This is our path for the Earth around the sun like this. So that's a revolution. And that's going to change. If we had no tilt in the Earth's axis, we would have the constant weather all the time. It would just be night and day, 12 hours of each all the time. But because we have this tilt, and the tilt of the Earth is what gives us our seasons. It provides a more uneven heating of the Earth's surface, and that's what we'll look at in the next slide here. But I wanted to show you one thing really neat that as we go through. As we look at our Earth is tilted at a 23.5 degrees. So we can see this tilt is right here. So north isn't straight up, it's kind of tilted away from the sun. Now, as you notice, we have a bunch of different lines here. We have our equator here. We have our tropic demarcation here, which is 23.5 degrees. Notice it's the same as our tilt. We'll talk about that a little bit later on. We have our 66.5, which is going to be basically the marcation of the start of the Arctic Circle. And then we have one down here, which is the Antarctic Circle. And we'll talk about the importance of these. Okay, so let's look at this tilt of the Earth, and it's going to give us 4 important dates a year, and these are our solstices and equinoxes. Let's start off with our winter solstice, which happens in December on the 21st or the 22nd. And we'll talk more about these a little bit later on in the course, but I want you to see why this gives us seasons. If you notice, and we draw on our equator, that we can look at any given moment, more of the northern hemisphere is going to be shaded. So it's going to be nighttime longer in the northern hemisphere than it is in the southern hemisphere. This we notice in wintertime. The days are shorter, and because of that, we get less heating. And the reason for this change is because our tilt to the Earth, where northern hemisphere is actually tilted away from the sun. So it's getting less sunlight, so that's why it's going to be cooler. The opposite of the winter solstice is going to be our summer solstice. And notice that that's here in June. And if we draw our line again, notice we have less nighttime than we do daytime. So now the days are longer. We're going to get more heating. So I kind of want you to see that it's the opposite. And notice in the winter solstice, we're faced away from the sun. In the summer solstice, our tilt to the Earth is pointing towards the sun. So we can see those variations. If we look at the summer or the southern hemisphere, in the winter solstice, our winter solstice, notice they have more sunlight. So they're going to have their summer solstice here. And then quite opposite, when we have our summer, that's when we're going to have their winter down there. So we can see that the northern and southern are going to be opposite. And we understand that because it's that tilt to the Earth that does so. Now we have 2 interesting dates. Those are our equinoxes. Equinox, the equa means equal, and the nox means night. And what that simply means that on March 21st or 22nd, which would be our spring equinox, and on September 23rd, which would be our fall or autumnal equinox, that's where the tilt of the Earth is pointing in such a manner that half the Earth is getting sunlight, half the Earth is getting darkness, and we have 12 hours of each on the equinoxes, and that's why it's called so. So these are 4 of our important dates, and we'll talk about those a lot later on in the course, especially when we get into astronomy real quick. So that's it for this video. As always, good luck on your quiz, and we'll see you in the next video. Aloha and welcome to our video on heating the atmosphere. In this video, we will describe heat, and we'll list the 3 major mechanisms of heat transfer. We'll also describe how the atmosphere is affected by heat transfer mechanisms. So before we go any further, let's talk a little bit about heat. Heat is a form of energy, and we can transfer that energy by 3 different methods. We have conduction, which is simply by touch. And most of this is going to be transferred from the molecules of one to molecules of another. So by touch, if the molecules of one has more energy, it's going to appear hotter, and it's going to have faster moving molecules. Those faster moving molecules will collide with the other object when they touch, and that'll cause the other object to heat up, like the spoon here we see in our container. We can also have convection, and convection is energy flow, and that's going to be in liquids and gases. So we call those things fluids. So it's a fluid flow transfer of energy as heat. And that's what we'll see in our atmosphere, where we have the gases and things like that. But we notice we also have space. And space has no gases. It's empty. It's a vacuum for the most part. So we have our third way of transferring energy, which we call radiation. And that's going to be like in the stream of electromagnetic waves. Okay, so we have this radiation, which is like our light energy, which is going to be transferred through a vacuum, and that's how energy gets to the Earth. We have our convection, which is what happens in the atmosphere, and that's where energy is going to flow. And then we can also have energy transfer from heat as conduction when 2 things are touching. Okay, so let's talk a little bit about radiation. Radiation from the sun comes to us in the form of electromagnetic waves, and we can see the entire spectrum ranging from gamma rays to shortwave radio waves, and we're primarily focusing with visible light. That's what we can see. Now, when we're talking about this radiation, we're talking that transfer of energy from the sun to the Earth through the vacuum of space. Okay, and there are 4 laws that are going to kind of govern radiation. First, all objects radiate energy. Hotter objects tend to radiate more total energy than colder objects. The hottest radiating bodies produce the shortest wavelengths of maximum radiation. So as they get hotter, the wavelengths are going to get a little bit shorter. And then finally, objects that are good absorbers of radiation are good emitters as well. So these 4 laws help us work with radiation. I just want you to know they're here. Primarily, I want you to remember that radiation is the way that heat is transferred from the sun to the Earth in the form of electromagnetic waves. Okay, so let's take a look at solar radiation, and that's what comes from the sun. Before we do, I want to explain 2 terms. They are reflection and scattering. Reflection is like a mirror. That ray is going to come in, and it's going to bounce off. It's just going to be reflected away. Scattering is when you have that ray of light come in, and then it's going to be thrown out in all different directions. So it's going to be scattered out. So those are 2 different things I want you to be familiar with. Now, this graph that we have over here, we have 100% of solar radiation, and then notice we have this 30% lost to space by reflection or scattering. This is a total. This isn't going to be part of what happens to the sunlight that's coming in. This is just adding up this part, and this part. Then notice it's 5 plus 20 plus 5. That gives us our 30. So we're just going to kind of get rid of this part so it doesn't confuse us. And what we'll notice is we have 5% lost by the atmosphere, 20% is reflected from the clouds, and then 5% is reflected from land and sea surfaces, and primarily that's going to be ice and our lighter colors. So 30% of the energy that comes from the sun is bounced back into space, and that's what this was telling me up here. The other 70%, 20% is going to be absorbed by the atmosphere and the clouds, and then 50% is going to be absorbed by the land and the sea. So we can see that 70% of the sun's radiation sticks with us, it heats us up, 30% is going to be bounced back. Okay, well, that's it for our video. As always, it'll go into a little more detail in the lesson, and good luck on your quiz. And of course, we'll see you in the next video. Aloha, welcome to our video on temperature controls. In this video, we'll analyze how the heating of land, water, geographic position, altitude, and cloud cover all influence temperature. We'll define what an isotherm is, and we'll compare the heating of land and water. Okay, so if we look at the Earth as a whole and then we start looking at its pieces and parts, we'll notice that this temperature variation occurs. So different parts of the Earth are going to be at different temperatures than other parts. And there are several different reasons for this. One of the primary ones is going to be this difference between land and water. If you notice, if you go to the beach in the morning time, the sand is cold and the water is going to be kind of warm. If you stay there all day, when the sun comes out, the sand heats up faster and gets really hot, and the water now appears to be cool, even though it might be the same temperature. What we notice is that land is going to change temperatures quickly. Okay, it's going to heat up faster than our surrounding water. So the water is going to take longer, and that's because water has a higher specific heat. So if I am an island surrounded by water, then I kind of have this buffering system that's going to keep the temperature about constant, versus if I'm in the middle of a continent surrounded by land, we're going to see greater fluctuations in daily temperature. Now, geographic position also plays a role, and primarily it's going to be how far are we from the equator. We're going to be warmer closer to the equator because we're going to average more daylight per year than we would if we were up at the poles. Okay, so we're going to see a little bit of difference that way. Altitude also plays a factor. Remember, we talked how we live in the troposphere, and the higher our altitude, the cooler the air temperatures are going to be. So that's going to make temperatures a little bit cooler that way. We also have this cloud cover or albedo, and what that's going to talk about is if we have clouds over us, the albedo is this reflection of the light off. So we basically don't get the energy coming inside, so it's going to be cooler during the daytime, but also it's going to trap this heat trying to get away so it doesn't get cooler at night. So when we have cloudy days, our temperature tends to be a little bit more constant than it is if we have clear skies, where during the daytime we'll get a whole bunch of sun and heating us up, but at nighttime we lose a lot of energy during a clear night. And then finally, we talked a little bit about currents, and if we bring warm water up, then what are we doing? We're heating everything up, and remember, water is going to work as a buffer, and the same is true if we bring cool water in as well. It'll be a little bit cooler that way. So we have a lot of different reasons why temperatures can vary, and in the lesson it'll go over these in a little more detail. I just wanted to give you a quick overview. So let's take a quick look at this map of global temperatures in July. Now we have a little word here called isothermal. Iso is the same, thermal refers to temperature. So what this is going to show me is all of these different colors are going to be about the same temperature. So at the line here, everywhere on this line that you see that I drew a little bit of, it's going to be 20 degrees centigrade. A little bit above it to the north, notice we have a 10 degrees centigrade. So in between, we're going to have the 11s through 19s. And then we'll notice the same as if we go down, we can see that we're going to have the 21s through the 24s going to the 25 isothermal line. So isothermy is the same line, and we can kind of see, and we understand this one. We notice that we have the equator, which is going to run roughly right in through here, and this is going to be what we notice as the warmer part, because that's where it's getting the most sunlight, as the equator would be. And the further we go up or down, north or south from the equator, we're going to see a variation. Now, this being July means it's summertime in the northern hemisphere, so we're going to expect it to be warmer, and we can see that as we go up. Notice we have very little zeros here. We have a bunch of 5s, 15s. But if we go to the south, where it's their wintertime, we can see that there's a broader area of 0s and 5s, and then we even get some -10s and -20s because it's wintertime there. So we can see this fluctuation from the seasons as well. Okay, so that's it for this video. As always, good luck on your quiz, and we'll see you in the next video.